Example 5, we want to consider the equation 2 cosine x plus sine x is equals to 1. Part 1, we want to let 2 cosine x plus sine x be equals to b cosine x minus theta, and we want to show that b is equals to root 5 and theta is equals to inverse tan of half. So if I start off with this form, okay, so if we let 2 cosine x plus sine x be equals to b times cosine x minus theta, then expanding this expression, we're looking at b times cosine x times cosine theta plus sine x times sine theta. And the whole idea of using this form is because we've got some loss of cosine x plus some loss of sine x, and expanding cosine x minus theta, we're going to get cosine x plus sine x. Okay, so that's essentially the whole idea. So upon expansion, we can see that we've got b cosine theta, lots of cosine x, plus b sine theta, lots of sine x. And obviously just equating the left-hand side and the right-hand side, we can see that b cosine theta, lots of cosine x must be equals to 2 lots of cosine x. So b cosine theta, okay, b and theta are both constants, has to be equals to 2, and b sine theta lots of sine x is equals to just plus sine x. So that tells us that b sine theta itself has to be equals to 1. In using these two conditions, we want to show that b equals to root 5 and theta is equals to inverse tan of half. Right, so we'll call this equation 1 and we'll call this equation 2. So if I take equation 2 divided by equation 1, okay, equation 2 divided by equation 1, that shows that b sine theta over b cosine theta is equals to 1 divided by 2. So naturally, in this case, the b's cancel out. Sine theta over cosine theta, that's just going to be tan theta, is equals to half, which is why theta is equals to inverse tan of half. And now if I want to find the value of b, I'm going to start by taking equation 1 squaring it, equation 2 squaring it, and then I'm going to add the two expressions together, because cosine squared plus sine squared on the left is going to turn into 1, okay? And that effectively eliminates theta. So equation 1 squared plus equation 2 squared. On the left of equation 1, that's going to be b squared cos squared theta. On the left of equation 2, that's b squared times sine squared theta. And then on the right, I'm looking at 2 squared plus 1 squared, right? So if I take the b squared out on the left, I've got b squared brackets cosine squared theta plus sine squared theta, and then on the left, 2 squared plus 1, that's just equals to 5. And we all know that sine squared plus cosine squared is equals to 1, which means that b squared is equals to 5, and that's just going to tell us that b is therefore square root of 5. Okay, and this shows that theta is therefore inverse tan half, and b is equals to square root 5. Now from this, part 2 now wants us to hence find, correct to the nearest minute, where necessary, the solutions of this equation, 2 cosine x plus sine x equals to 1, for x is between 0 and 360, right, as usual. So we know that 2 cosine x plus sine x could be rewritten as b times cosine x minus theta in part 1, and we found b to be equals to root 5, and theta is equals to inverse tan of half. So we're going to say that 2 cosine x plus sine x can be re-expressed as square root 5 times cosine x minus theta. Now theta we said is equals to inverse tan of half. Now this is not going to be a special angle, so therefore if I type it into the calculator, this is going to be 26 degrees and 34 minutes to the nearest minute. So therefore just substituting this in, okay, we've got 26 degrees and 34 minutes replacing theta. So if I know that 2 cosine x plus sine x can be rewritten as root 5 cosine x minus 26 degrees and 34 minutes, then solving 2 cosine x plus sine x equals to 1 is the same as solving square root 5 times cosine x minus 26 degrees and 34 minutes, right? So I'm just solving this to be equals to 1. So in other words, cosine x minus 26 degrees and 34 minutes is equals to 1 over square root 5. Okay, and our acute angle, our acute x minus 26 degrees and 34 minutes is going to be shift cosine 1 on root 5. So acute angle, in this case, is going to be equals to 63 degrees and 26 minutes. Now take note that we want to solve cosine of our angle to be equal to a positive value. So if we look at ASTC, that means that our solution is going to lie in A and it's going to lie in C. So the real x minus 26 degrees and 34 minutes that we're looking for, okay, the first solution lies in the first quadrant, so that's just going to be the acute angle itself. And then the second solution lies in the cosine quadrant, so that's going to be 360 minus our acute angle. So that's going to be 296 degrees and 34 minutes. And now to find x, I'm just going to add 26 degrees and 34 minutes to both sides. And that's going to give us x is equals to 90 degrees, right? 63 degrees and 26 minutes plus 26 degrees and 34 minutes is going to be 90. And 296 degrees and 34 minutes plus 26 degrees and 34 minutes is going to give us 323 degrees and 8 minutes. Okay, so these are the two solutions for this equation, right? And this is another demonstration of how we can use auxiliary angle method to transform an expression, okay, that is a linear combination of sine and cosine into one trigonometric variable. And to solve these equations, right, we just use the transformed form and we just solve that to be equals to whatever we have on the right hand side. Okay, and the most difficult part about this is obviously just the transformation itself, right? So that's what we're doing for part 1 over here. Okay, and as I mentioned in example 4, make sure you guys think about why we use specific forms for specific variations of linear combinations for sine and cosine, right? So think about why in this case, why is it that when we have a cosine x plus b sine x, that we use cosine x minus some angle, right, to represent the compound angle. So that being said, this concludes example 5.